Hello, hello, hello. Welcome back. It is Tuesday, the 3rd of February, and today we are going to go through the experimental physics stuff. So this is kind of on the recommendation of one of my students who said that experimental physics is something that would be good to cover. I completely agree. I completely agree because it's A, one of my absolute favorites, and B, I find not sort of rigorously done in a lot of classrooms. So it's something that a lot of people come to me and ask me for, both in the IB and in the A level. So what I'm planning on doing today, and also just sort of a broader schedule here, my Tuesdays are looking very open at the moment, which means I think I can afford to do like a double stream on Tuesdays rather than separate streamings. So I can do like a paper run in the morning, and then in the evening, I could do a sort of normal lesson that people can actually attend because you're not in school, going through the lessons from that paper. So for instance, today I'm planning on doing an experimental physics double. So paper in the morning and then live stream in the evening, going through some of the concepts that we're seeing. So the runs are going to be as usual, going through concepts, but also really going through exam technique. And then in the evening, we can go through more of the theory that a lot of people struggle with, not just the stuff that came up on the paper. So today I've got AQA's paper 3A. This should still be relevant, even if you're doing different boards, including IB, because at a certain point, the physics is the physics, right? It's just going to be the examinable stuff that comes up across the board. It's going to be error analysis. It's going to be taking a model and turning it into a straight line to plot, all the usual stuff. And also exam technique at a certain point is just kind of universal. So without much further ado, I expect today will probably be low attendance and I'll just be able to get the run done. I need to separate this out. So apologies for not having that prepped, but the papers are good to go. My timer is good to go. My pen tablet is about to be good to go. And I'm gonna just get everything aligned, start sharing my screen, and then we can get going. So, come on, pen tablet, you can do it. Technology hates me so much. So for this paper, you're advised to spend 70 minutes on the section, so that's how much I've put on the timer. We'll go through it, we'll mark it up, we'll see how it goes. So, 3, 2, 1, begin. Okay, so resistivity of a wire, classic. Screw gauge micrometer, love it. State in millimeters the resolution of the main scale. The resolution, oh, can I remember this? This is annoying. I think it's 0.01 millimeters. Let me check. That's because this is 5 points. Yeah, it measures it in millimeters. And that's specifically, 0.01, I'm going to say. So 1.1, the resolution is plus or minus. So the resolution is the smallest thing that it can measure, which I think is 0.01 millimeters, which is what one of these small increments represents. What is the reading on this micrometer? Well, also, look, it tells you. You can see the exam technique. Even if you couldn't remember that, let's look at this. This gives you the answer. It's plus or minus 0.01 millimeters. That's the precision of these. So what does this read? This reads 6.5. So that would be 6.712. So 6.72 millimeters. Now, the way this works, so that's 5, 5.5, 6, 6.5, and then you add on what you see. So it's 6.5 plus 0.22. So it's 6.72 millimeters. There. Okay, a wire is placed in the gap between the anvil and the spindle. I haven't even read the premise of the question, which was silly. So, okay, so a wire is placed in here. State and explain how this gap is closed just before taking a reading. So what you do is you turn the thimble until you're kind of close. I don't know the exact wording on this, but you turn the thimble until you're close or kind of in contact. But you don't want to overscrew it. So you and then you turn the ratchet until it starts to click. And so close, turn ratchet until it clicks, or it slips. And what that does is it prevents you from pushing the spindle in too far. And causing it to sort of contract or compress the wire, which would alter the reading and make it seem smaller than it is. So I'm going to write that down just so I have a little note to myself if that's what I wanted to say. Although it seems like a lot for 1 mark to have to state and explain, but whatever. Okay, so 2 terminals are used to mount X on a ruler. Clips are used to connect a voltmeter across the 1.2 ohm resistor. When the switch is closed, the voltmeter reading is 931 millivolts. So we know the resistance across that, so we know the current through that. Okay, so let me have a think about this. 1.4. When the switch is closed, voltmeter reading is that. Let me read. Okay. It's wire X. What's the 1.2 resistor? Okay, so we don't know. So we know the current, certainly. So for the first one, current is V over R, which is 0.931. Especially in this paper, being extremely careful with units is super important. That includes any axes, by the way, of any graphs. So the current is 0.7758 amps. And then we know this voltmeter reading. So R equals V over I for this other thing. And the volt, it's 0.397 all over 0.7758. So that answer. So 0.397 divided by answer, we get 0.512 ohms, which is approximately 0.5 ohms, which is good. Okay. So the length of the wire is L, R. So we know R should be directly proportional to L. So determining the resistance per meter, this is... Okay, in the real thing, you would be able to annotate on... Oh, but I don't have straight line on this. No. Okay, so what am I going to do? Did not think this through. How am I going to annotate? All right, here's what I'm going to come over here for a second. I'm going to see if I can draw straight lines. No, okay, so let's stop the screen share for a bit. I'm going to pause the timer and let me just sort this out. Apologies for that interruption. So I just had to update some of the tech real quick. And now I think what I'm going to do is I'm going to carry on in this way. I can actually now annotate directly onto the thing, which is very convenient. And I can also draw straight lines. Okay, so cool. That was my test run. What I'm going to do now, so this is sort of, you're going to have some plus minus on this. But let's say I drew this as my, although in fairness, I think I can actually do a little bit better. I think if I go something like this, the point is equal points above and below. So 2 are above. This is kind of, this is there or thereabouts, because there's a plus minus on it. I'm going to go with that line, maybe. And so, okay, great. What I got to do now is find the gradient. In order to find the gradient, what you want to do is draw your triangle as big as you possibly can through points that you can identify precisely. So here, let me look for candidate points. I see that's one that looks like it goes right through a square. And where else do I see it? Sort of one up here. That looks like it goes right through. Apologies if the sound went weird for a second as my face literally went through the microphone trying to actually see this. All right, so drawing your gradient nice and big. Change in resistance is, oh, well, that's 0.65. That's 0.375. So 0.65 minus 0.375 gives a change in the resistance of 0.275 ohms. Change in length, note that it's in millimeters, that's 375, 380, that's 390. So 0.39 meters minus this guy, which is 0.22, which is 0.17 meters. So the resistance per meter, oh, I forgot to start the time again. So the resistance per meter is 0.275 all over 0.17, which is 1.6. No. Right. Okay. So what I should be doing is not annotating on that. So that won't be permanent. That's fine. But okay. So 0.275, okay. So from here, it's 0.275 all over 0.17 is 1.6 ohms per meter, which I think is the answer there. Resistance per wire. Resistance per meter of various metal wires. The diameter of X is one of the D values. We don't know which one. Okay, so one of them is 1.6-ish. Okay, so that's nichrome. That's this one. So the metal is nichrome. And the resistivity is AR over L. In other words, R is equal to rho over A times L. And we said that the resistance per meter, the 1.59 I'll use, is rho over A. And so to determine the resistivity, we know that rho is equal to 1.59 times the area, which is pi, times the radius squared. And the radius is 0.93 over 2 times 10 to the minus 3 squared. And if I run all that in a calculator, I get a value of, so 1.59 times pi times 0.93 all over 2 times 10 to the minus 3 all squared. And I get 1.08 times 10 to the minus 6 ohms. Oh, what's the unit? Ohm meters. And I got the unit there I got by saying it's resistance, which is ohms, and then area over length is meters. So it's ohm meters. A student adds error bars for R and L to each point. She estimates that each value of R has a percentage uncertainty of 6. I love percentage uncertainty. Let's go. Each value of L has an absolute certainty of 5 millimeters. So R and L. Um, 209,388. That's 209. That's 388. So R is absolute 5 millimeters. So they're equal widths, certainly. Because they're just plus or minus 5 millimeters on both of them. But the heights are going to be different. So the percentage uncertainty is 6%. So here, it's 0.35. And we want to find out what 6% of that is. So that is 0. So in other words, it's 0.35 plus or minus 0.021 or 0.02. And then on the other one, if we scroll up, we can see this guy is 0.655. No, 65. 0.05, 0.0, so 655. Yeah. Something like 0.64. These ones are gonna be bigger. So the at L equals 388 millimeters, error bars are bigger. Vertically, same horizontally. And for measure, just so I can get any sort of mark, 0.6. I'll call it 0.655 times 0.06. So 6% of that is roughly 0.04. So in other words, it's 0. So we can see it's in fact about double. So maybe I can do even better there. So it's bigger vertically, and adding to that vertically, it's almost twice as big. Twice as tall, sorry. Okay, so that feels like a lot of things I can say. It was only 2 marks, but I don't know exactly what they're going for, so I'm just going to write a lot and hope I actually get the marks in the mark scheme. How error bars are used to determine the uncertainty in the gradient of a linear graph. You can get the line of max gradient through all error bars. And you compare that. Oops, can't spell. So the line of maximum gradient through the error bars, you can get the line of minimum gradient. And then the uncertainty is max minus min over 2. Okay, so question 2 now. Shows apparatus used to investigate how the resistance R of the LDR varies with illumination. Okay, so we've got set to different ranges. That's the ohm meter set to different ranges. Okay, so we can adjust the sensitivity. Why the reading displayed in figure 6 shows that the ohm meter is set to range C. Okay, so it's reading 2.84 ohms. No, it's measuring 2.84 somethings. Well, first of all, it can't be A because that has the wrong precision. So we need one with 2 decimal points, and only C has the correct precision. So it only C has the correct precision of plus or minus 0.01. So the quantity EV is a measure of the intensity of the incident light. The resistance is given by that. In figure 6, well, it's understanding that that's kilo ohms. So the actual resistance is 284. Yeah. So log of 284 equals minus 0.772 log of EV plus 5.09. And we can rearrange this to solve for EV. So log of EV is 5.09 minus log of 284 all over 0.772, which when I run that in my calculator gives me log 10 of 284 all over 0.772. We get that the log is 3.415 and EV is 10 to that thing, which is, no, I got that wrong. Well, I got that very wrong. Why did I get that very wrong? So we know from certainly that it is set to range C, which measures it in kilo ohms. So it's 2,840. Right. Okay. Apologies. Let me rerun that. 5.09. So I knew that luckily it was a show that. I shouldn't have made that mistake though. So that was exam technique because I was transferring a reading but sort of doing it improperly. And those really annoying things are exactly the kinds of things that can trip you up in the real thing. And that's why I like to do these runs, by the way, is to make sort of instructive mistakes. So you guys pick up on like, oh yeah, these are the kinds of things that can happen. And like, this is how to avoid it when I'm doing my actual run. So it's 131.8, which is approximately equal to 130 lux. Okay. It can be shown that EV is proportional to 1 over x. How would you confirm this relationship? This is a classic. So the way to confirm this is to, if you plot log EV against log x, it should be a straight line with a gradient. Now, what this does, by the way, if you plot by doing logs of both sides, with gradient minus 2. The reason for that would be EV is equal to k over x squared, which means that log of EV is minus 2 log x plus log k once you go through all the power law stuff. I'll do that when I'm sort of marking up and doing the run. But if you're ever testing for a power law relationship, a log-log graph is exactly how to do that. You do not need to show any calculations, but like it will be useful after the fact. So deduce the value of x when E is 130 lux. The value of x. Okay, so deduce the value. So I have this graph. Deduce the value of x when E is 130. Oh. That's not on the graph. I suppose we can use this to find the constant of proportionality. So here we know that, so if E is proportional to 1 over x squared, we know that E is equal to k over x squared, which means that EX squared is a constant value k. And we know that here 1200 times, so that's each of those represent 50 divided by 10 is 5. So each small increment is 5. So that gets me up to 210 millimeters. I will not fall for the units trap. I will not fall for the units trap. Equals k. So that constant k is 1200 times 0.21 squared, which is 52.92. Now, in the real thing, I'd be flipping back and forth and making sure this went in that answer bar, but whatever. So 52.92, and I want to just verify that against another point if I can. So I will pick this point here and check that 400 times 5, so 365 times 0.365 squared is 53.29. So k is roughly 53. So that's from this point here. That's kind of what I'm getting. So let's use k, because these agree that k equals 53 to two significant figures. So 130 equals 53 all over x squared. X squared is 53 divided by 130, which is 0.408. X is equal to root of that, which is 0.6385. Or in other words, I'll call it 640, corrected 2 sig figs. I have a feeling I need to make some slight tweaks on that when it comes to like marking it up, like exactly what they wanted. But I'm happy with that as a broad method. And by doing mark scheme analysis, we're going to learn exactly what they want you to do. So that's why like mark scheme analysis will lift you up an entire grade boundary as you move through towards the exams. So R is measured when X is 450. Figure 8 shows how the ohmmeter displays the values of R when set to the ranges B and C. The uncertainty of the reading on the ohmmeter is plus minus 2% of the displayed reading plus minus 2 in the least significant digit. Okay. So here 1.02. Okay. So reading the question, kind of getting to grips with it. Complete table 3. So they're just teaching me something on the spot and getting me to use it. So on range B, which is this one, we have the minimum will be 0.98. Whoop. So 0.98 times the 1681, and then knock off 2 on that. Will be 1645 ohms on the minimum. And on range C, the maximum will be 1.02 times 1.68 plus 0.02 times 1.68. So this is 1.73 kiloohms. Okay. The lamp and the ammeter are switched on. R is recorded with different numbers of slides placed on the LDR. Now, placing the slides, I imagine, will decrease the light intensity. The positions of the lamp and the LDR are not changed. Identify two other control variables. Let me check if... God, okay, so you want to make sure that any changes in resistance are due only to changes in light intensity. By controlling the positions, that's controlling light intensity. I'm going to suggest that the thickness of... Let me... Hold on a minute. This is interesting. How am I going to... Well, everything is the same. Well, we'll say the same lamp. So it's emitting the same... so it's the same emitted intensity. What else? I can't think of anything off the top of my head, you know. So in the absence of anything else to say, I'm going to say the thickness of the slides, but I don't like that. I don't like that at all because that's... Control variables, yeah, things that you keep the same because otherwise they would impact it. Wait. What if it was made of the same glass? So like maybe different glasses absorb different amounts? So maybe I'll say this, the slides are the same type of glass. For instance. Ooh, I don't like that at all. I imagine I'm going to dock a mark there. Hello! Hello to Notkraken. Yeah, today's experimental physics day. Hope you're excited about it. So for the arrangement in figure 9, it can be shown that this relationship is true. Explain how this can be determined. Again, this linear graph, they love asking about it. So in this case, we're going to take lns of both sides. So ln EV equals ln for 100 minus mu n. So in other words, different glasses do absorb different amounts of light. That may be true, but let's see if it's in the mark scheme. Because again, this is not to be too cynical about it, but exams are not about being right. Exams are about picking up marks, which only happens if you write what they wanted you to write. So it's learning how to play that game, which is what I'm trying to demo right now. So in this case, if we... Yeah, your tutor always says that. Hey, listen, we go into tutoring, not teaching, because we love that exam game. So here, that means that ln of... I'm now... If this is Dean... No, it can't be Dean, because you're in school. I have this constant game where one of my students says he logs in on a bunch of different alt accounts and leaves comments trolling me. So every time someone comments now, I'm like, is it you? Apologies, you're fine. Okay, so this is, in other words, minus mu n plus ln 400. And the reason why I rewrite it like that is because then it's of the form y equals mx plus c. So in other words, a graph of ln of EV versus n is straight line. Nice. Is straight line. and the gradient is minus mu. So in other words, mu is minus the gradient, and then that's fine. So in an experiment, mu is that. Deduce the minimum number of slides needed to reduce it by 50%. Okay, so n is the number of slides. Oh, if n is the number of slides, then absolutely, then you also want the same thickness. Because if you're not measuring the thickness, if you're just measuring the number, is recorded with the numbers of slides, then it has to be the same thickness. So I'm going to go back and change this. In fact, I'll just add it, and same thickness. They can't, because in terms of playing the exam game, they can't. They can award you, they don't do negative marking. So they wouldn't go, oh, this part of it's wrong, but this part of it's right, so I'm not going to award the mark. It's very rare for that, and they'll specify. But I think adding it for a belt and braces approach should be completely fine there. So reducing EV by 50% means that, well, obviously when n is 0, then EV is 400. So when is it 200? It's really just saying that e to the minus mu n equals 0.5. So e to the minus 9.0 times 10 to the minus 2 times n equals 0.5. Take logs of both sides. So n is equal to ln of 0.5 all over negative 10.0 times 10 to the minus 2. And that is, I imagine, not going to give me a very pretty number. Ln 0.5 all over negative of 9, 10 to the minus 2 is 7.7. So in other words, the 7 doesn't get you there. You can't have 7.7 slides. So minimum 8 required. Okay. Okay, so question 3 is the method. How am I doing on time? Okay, so I got time. Question is about a method to investigate how the force on a conductor varies with flux density and current. God, I hate this experiment. Okay, so how a rod clamped. So you have a copper rod. Describe a method to show that the copper rod is horizontal. Your method must include the use of a meter rule. You may annotate. So this is set squares. Is it set squares? Okay, so 3 marks. And again, this is probably something you've like memorized. Could you check the heights of the, yeah, you probably could. I suppose it wouldn't really help if the table itself wasn't horizontal though. But you could absolutely, if I annotate it, you're measuring meter rule. That's terribly drawn, but whatever. So you can measure the meter rule in 2 different positions and show that they're the same height. Oh, but maybe you want to use a set square for parallax error. Or maybe you want to use a mirror. So I'm going to say record height on both sides should be same. And maybe, because this is definitely going to be asking about how to reduce parallax error of that reading. So maybe you want to do use set square to avoid parallax error. I feel like I'm going to lose a mark on this just for precision of what they want. What else do they want here? I think I'm not too enthused by that. I hate that. Shows the copper rod positioned above a digital balance. Two identical magnets are mounted on a steel yoke, opposite poles facing each other. So there's a uniform magnetic field in between. So that's the copper wire. The yoke is then placed on the balance so that a uniform magnetic field is applied perpendicular to the copper rod. When the switch is open, the reading on the balance shows the mass of the yoke and the two magnets. When the switch is open, it shows that. Okay. When the switch is closed, the reading on the balance decreases. So that means the force felt must be upwards. When it's closed, we know the current is going in this direction. So therefore, the left-hand rule, so force up, current to the right, and by Fleming's left-hand rule, if the force is up and the current is right, then the magnetic field is into the plane of the paper. So into the plane of the paper. Okay, so here, what do we got going on? So the current is varied. The balance reading is recorded for different values of I. The switch is opened, which means you stop the current. Two additional magnets identical to those used before are attached to the yoke. So it's on the other side now. That's what's different. The force on the rods would be downwards. Not the magnetic force, because you can see the reading on the balance decreases, which means there is less downward force. So when this force acts, it decreases the resultant downwards force. The weight is downwards, but the magnetic force from Fleming's left-hand rule is upwards to make the reading on the balance decrease. Now, with four magnets attached to the yoke, how put it? So here, I'm just trying to work out what they're telling me about these magnets. Two identical magnets with their opposite poles facing each other. Will this actually strengthen the magnetic field? Well, clearly. M2 is the one with more magnets, right? Yes. So more magnets, steeper gradient. Cool. This is the problem with this paper as well. You're constantly like flicking around, moving around, trying to like understand what's happening. It can be shown, okay, this relationship. Deduce the fundamental base units for K. Interesting. So these are all masses. The fundamental base units will be kilograms. We know that F equals BIL, which means that F over L equals BI. And a force is kilograms meters per second squared all over meters equals BI. So therefore, BI has units of kilograms per second squared. So K is kilograms, which is the mass, when you can put those all over to the left-hand side, divided by BI. So divided by kilograms per second squared. So K must have units of seconds squared. So fundamental base units are second squared. Determine Y is the mass in grams of the yolk. N is the number of magnets, which changes from 2 to 4. Okay. When the current is 0, okay, this isn't too bad. So we know that 135.2535 is 4z plus y. And we know that 134.85 is 2z plus y. So let me write this down. So 135.35 135.35 is equal to 4 times the mass of a magnet plus the yolk. And it was 134.85. It's 2z plus y. Just simple simultaneous equations here. Let's double up the bottom one. So 134.85 times 2 is 269.70 is 4z plus 2y. And then you subtract these equations. So that minus 135.35 is 134.35. Or another way to consider that is that goes down 0.5 when I subtract 2 magnets. So if I go down another 0.5, I should get rid of those 2 magnets. So the yolk is 134.35 grams. Student sets up the apparatus with the copper rod positioned incorrectly, not between the magnetic field. So there's no magnetic field on that. Or maybe it's weaker. Maybe it's not uniform. Compare the student's graph with the graph of M1. Explain your answer. I'm going to say it's not in the magnetic field, so you wouldn't get variation. Although I can see this is why I hate this paper, is because, like, are we going to argue that the field is weaker, or are we going to argue that the field is 0? Because it isn't between, we know there's a uniform magnetic field between 2 magnets. I suppose we wouldn't argue it's 0, though, because I suppose we would argue it would be uniform in between, certainly. I think there would be some out here. It would just be weaker. So I would argue there's still field, but there's less B, but B is decreased. Now, what that's going to do, based on this, is it will therefore decrease the gradient. But, so same intercept, but less size of the gradient. So decreased magnitude of gradient. I say decreased magnitude because it is a negative gradient, right? So if you say that's decreased, does that mean it's gotten more negative? Like it can just get a little bit trippy. So I'm going to say decreased magnitude of the gradient, but the same intercept. And the same intercept because then that term will be 0. So I think I've got an explanation here. What that does to the gradient, what that does to the intercepts. I think that's the 3 marks. No, I may as well. Why is it the same intercept? Because same 2. Was it 2z plus y when I equals 0? Something like that. Just to make sure I pick up that mark. And, ooh, paper done. So do I want to check anything? Is there anything I'm not convinced about? I was happy with this. I answered these on the mirror board. That was fine. That was fine. Fine. I don't think watching me check work is going to be any good, but I should check to make sure I've answered every question. I should always do that. I'm confident on how I did that. So this actually didn't feel bad. I know I've seen some like horrible paper 3s. So in the grand scheme of things, 2024, not that bad. Apart from this question, which I hated. I'm sure I'm going to lose marks there. All right, I'm going to stop the time there. We're going to mark it up. So I had 23 minutes left to go, which is good because I could have used that time in the real thing on the... hold on a minute, let me get the mark scheme open. You could spend that time on your optional in this particular paper if you're doing AQA. So here, what I'm going to have to do... Oh, I got that wrong straight off the bat! No! Man, I can't believe I fell for that. So what I'm going to do as well is I'm going to stop sharing there. Well, actually, no, what I should have done. Let's keep sharing the entire screen. But what I'm going to have to do is to compare this with this, but make it the mark scheme. Oh no, the mirror whiteboard is what I needed for the first part. So you can see right off the bat, I said it was 0.01 millimeters, but it's not. It's 0.5 plus or minus 0.5 millimeters. This correct answer only. That can't be correct, can it? How is that right? Oh, the main scale. I'm wondering if that's okay. Oh my God, I didn't read the question. Stupid exam technique. Bad. That's the main scale. That's the micrometer scale. That was totally available to me if I had actually paid close attention to the figure. So yeah, exam technique, showing you the tiny little things that can go wrong. So the main scale is so yeah, these are 0.5, and then you add the 0.01 from the micrometer. It's specified main scale. Sneaky. All right, 6.72. Use of ratchet or use of thimble and then ratchet with valid justification, which is my go-to. Yeah, consequences could cause it to be distorted. Compressing the wire, exactly. Cool. So running this through, you get 0.51, which rounds to 0.5 as required. Perfect. And then that was when I transitioned to here directly. So here, ruled line of best fit, gradient evaluated. Now, look at this. So you need to have large values for delta R and delta L. And if I come back to here, I should, if I open this up, still have this on. So yeah, delta R was 0.275, which is bigger than that, and delta L is bigger than 150. I used 170. So you want to use a triangle that covers at least 2/3 of the data, and I picked points that I could 100% certain. In fact, I could even have used this one right at the bottom and would have been completely fine. Okay, so attempts to find px. So it is nichrome, certainly. Now, what did I find? I said 1.08 times 10 to the minus 6. Boom, that is in range. Allow more than 2 sig figs that round to 2 sig figs in that range. Good. And I've got ohm meters for that mark. Good. Okay, so I've got full marks on that part. Great. The horizontal error bars are the same, but the error bar in the vertical, about twice the length of the first. Perfect. Is exactly what I said here. So look, they didn't just want bigger, they wanted some calculations for this mark. So if you've got data, use data is a really good strategy. So we've got our uncertainties. We're comparing them, and they're about double. Great. I love that I went back and added that. I didn't just say bigger, I also calculated. And the context clue there is they've got all this empty space here, which implies they want you to use it to do calculations. So doing the calculations and then talking about the fact that the error is about twice as big. 1.8. I need to have maximum gradient, minimum gradient, using lines that pass through all the error bars. Line through all error bars, great. And max minus min over 2, perfect. Okay. C, because it's 2 decimal places, great. 132. Yep, so that rounds to 132, which is approximately 130. Great. Damn it. Reads off from at least 3 different points on the line. On 2.3. Oh, no, that's fine. So EV, log plot should have a gradient of -2. Log gradient -2, perfect. Okay, so here, 2.4. I got 640. Brilliant. 2.5. $16.45, 1.73, perfect. Oh, I didn't read the question, guys. Go on to explain whether range B or range C should be used to measure R. Before you move off a question, make sure you've actually reread the question to make sure you've actually answered it. I fell for that because I thought those 2 things were 2 marks, so I thought I was done, but I did not reread the question. Go on to explain whether range B or range C should be used to measure R. When X is 450, R is, well, that's E. I would say range B because it has the smaller percentage uncertainty. And then you can calculate those. Yeah. Okay. So then here, I'm just annoyed at that little exam technique slip there. Hello, hello, hello. Hello to KK Official. How you doing? You missed my run, but it's all right. We're just marking up now, and then I'll sort of also be available to answer any questions. I'm also going live this evening if you want anything particular on these sorts of questions. Is this Physics M? So this particular test that I did is AQA A-level physics, but the practical physics will be valid across whatever board you're doing. So this will also be true in IB. I have a bunch of people doing IB physics, and we do all this kind of stuff, and it will be true of any A-level as well. So it's specifically the experimental physics paper. Okay, so what did I say for 2.6? What grade physics is this? This is A-level IB. So this is your final year of high school, that kind of thing. So for 17, 18-year-olds. So you want to keep the light level in the room. That was a great one I didn't think of. Thickness of the glass slides. Great. The brightness in the lamp. Allow intensity from the lamp the same. Oh, I'm so glad I added that. Same emitted intensity. So what we're doing here, apologies for, let me catch you up. So the premise of this question, this is all about experimental physics. And the premise of this question, we were doing a whole bunch of stuff, but now we're measuring how the light intensity from this lamp affects the resistance read on the light-dependent resistor when I put glass slides in between. The glass slides will absorb some of the light, and when the light intensity decreases, the resistance will increase, which is what I should measure. So the light, same emitted intensity and same thickness of glass slides got me the marks there. So I'm glad I over-explained it because my primary answers would not have got those marks. So then here, if we have this relationship to get it into the form of a straight line, let me just check I did that correctly. So you plot ln EV against n. And it's a straight line, and mu is the negative gradient. There. Cool. In this experiment, minimum of 8 slides. Perfect. Ooh, no comments. No comments. I did not like 3.1. I'm really curious to see what they say. So going through 3.1, you wanted to use, they wanted the experimental protocol for measuring and making sure the copper wire is horizontal. Now, by the way, this is all stuff like you have 12 required practicals in AQA A-level physics. You will also have required practicals in whatever board you're doing. Those practical protocols you should memorize before going into any practical paper, because the techniques that you learned, the techniques that you did, you may get asked to write down, as is the case here in 3.1. Now, obviously, I have not done one of these practicals in a while. I don't have these all memorized. This is rote memorization. So I'm probably not going to do as well as that. Oh, you're 10. You think you can understand some of this? Okay. So if we have more of the number of slides, then that means the resistance increases and the light intensity decreases. Correct. So going back here, just to explain that if you're interested. So here, what we want to do, so this is, by the way, if you really want to get the basics of any experimental physics, right? The point here, when we're talking about, let me talk specifically about this question. If we're talking about control variables, in any experiment, you want to know that the change you're measuring is only due to the thing you're changing. So in this case, we're measuring resistance and putting glass slides on. So we want to set up the experiment to make sure that any change in that resistance is only due to the glass slides and not something else. And so what you need to do is to think of anything else that could affect the experiment and make sure it stays the same. So the only thing that changes is the glass slides, and that's the only thing controlling the resistance. You You can have the initial intensity by putting no glass slides on. That would be a perfectly valid way to do this. And in fact, you can see that they do. Oh no, they don't show you a graph on this. But you're right, you would do it for n equals 0, and then keep on adding more glass slides, and then measure the resistances at all of those levels. And as you add more glass slides, the intensity making it through decreases, so the resistance you would expect to go up. Do they show you the formula here? They do show you the formula, which, again, if you're 10, you probably haven't seen this exponential before. You might have done. But you can use mathematical tools in order to get this into a straight line, because all of experimental physics is about forming a straight line, because that's the one that's easiest to see. If things are all curvy, you don't know exactly what that relationship shows. But as soon as you get it into a straight line, you look at that and you know it's a straight line, and you can measure the gradient and the intercept and get useful information from that. Is that Euler's number? Yes. Yes, it is. 2.7 something, something, something. You use that a lot in the A-level syllabus. And you will see that number come up wherever you see exponential growth or exponential decay. So then here, got the minimum of 8. So going back here to the 3.1, talking about this protocol, which you have to just sort of memorize. Measure the height from the bench to the rod at a number of different points and check the heights are the same. How the ruler is made vertical. Expect to see set square, and this is a technical language that I didn't write down that I needed. Expect to see a set square in contact with the bench and in contact with the ruler. Right. So I use a set square to, no, I got, okay. So what I should have done is had set square here to ensure that the ruler is vertical, and then measure that, make sure the height stays the same as you move across the wire. So what would I give myself there? Oh, 9th grade. So sorry, when you said you're 10, I thought you meant you were 10. Oh, wait, you are only 10. You passed your elementary, middle school. All right. You're well ahead of the curve. Nice. I only skipped 1 grade. You're way ahead. Okay. So yeah, keep asking questions. I'll keep answering them. In terms of exam technique here, though, what I'm trying to demonstrate is mark scheme analysis lets you know what exactly you need to do to refine your process to fit the particular exam you're doing. So in this case, yes, I kind of knew it, but I didn't study it in the specific detail required to get like 100%. Now, when I was in the trenches, when I was doing the exams, you better believe when I walked into a practical paper, I had every single step of every single one of those 12 procedures completely memorized, because that's what it takes. Now I'm kind of retired. I'm kind of more demonstrating the skills. I'm more interested in how to communicate how you can do your best. So that's what you would do. Just make sure your knowledge points are tip-top shape, ready to go there. Then here, moving on to 3.2. Huh. Why is the force on the rod downwards? That's what someone else said. Hold on a minute. 3.2. Well, I said the force was upwards. Because when the switch is closed, the reading on the balance decreases. Field out of the page. Oh. That's, am I missing something here? When the switch is closed, the reading decreases. Maybe I'm just completely misunderstanding this question. Are you a retired teacher tutor? No, I'm a retired exam taker. I am a full-time professional tutor. What I meant by that was like, so for me, exams were like my sport. I treated them like an athlete. So like I was the guy, like I got an average of 98% in year 12 and then went, I'm going to beat that, and then got 99% in year 13. Like that was just my thing. I really loved not just like exams, going for every possible mark. And to take yourself to that level requires some very, very specific training. And maintaining that level is not something that interests me anymore. So that's what I mean about retirement from like being a full-time student and like really going for the top grades. Now I just sort of, coach people on how to do that same thing. So in figure 11, what am I missing? So two identical magnets are mounted on a steel yoke. The balance is zeroed. Maybe that's what I missed. The yoke is then placed on the balance. No, so the ends of the rods are connected. When the switch is open, the reading on the balance shows the mass of the yoke. And hold on, we've got a model here, though. We can see it goes down. The reaction force between the thing and the scale pen balance decreases. I swear that means the force must be lifting it up. If you move the steel yoke, I'm guessing the field changes, field and mass decreasing it. There's definitely a field here, but I think I'm oversimplifying it. I'm not sure if it's because my brain just isn't working well today. Uniform horizontal magnetic field. I don't like, maybe like, hey, if this is actually really easy, please let me know. I don't know what I'm missing here, but the fact that I'm making this mistake means that other people must also make this mistake, right? I think I'm missing something about this interaction, because to me, the fact that that mass reading decreases means that there's a force lifting that off the balance. Like there's less weight. So you'd expect. Maybe I'm missing the connection, but like how it all links up. So there's a copper wire, copper rod, right? And two items mounted in a steel yoke. Oh, wait. Okay, so that's the steel yoke. So the magnetic field is going like that, and that's causing. Oh! I think I'm. Yeah. Wait, so what exactly is being measured here? The yoke is placed on the balance so that a horizontal uniform magnetic field is applied to the ends of the rod are connected. Okay, I think I understand what's happening. It shows the mass of the yoke and the two magnets. Oh my god. Okay, I think I understand what's happening now. I'm getting confused. I am correct that... Right. Guys, here's what I missed. So let's use our exam technique, right? This is the arrangement. So this is the thing that's being measured. We are correct that when you put current through this wire, the force on the yoke and the magnet, so this thing goes up, but that means the force on the copper rod goes down. I think this is a Newton's third law interaction. I think that the rod experiences a force downwards and the yoke with the magnetic fields experiences a force upwards. That's what I got confused about. I got confused about the fact that the magnets would exert a force on the wire, but the wire is not the thing being recorded on the balance. The yoke with the magnets is the thing being recorded on the balance. So for the yoke and the magnets to be experiencing an upward force, the rod is experiencing a downwards force. And that's what I missed. The force on the rod is downwards in order to make this happen. And the current is moving to the right, which means that the magnetic field is out of the plane of the paper. Okay. What we are measuring here is the mass of this thing. We are measuring the mass of this setup, the mass of this yoke with the 2 magnets on it. So I don't really think we consider it as a force coming from the copper wire, but like it is certainly Fleming's left-hand rule. So that was an interesting question. No shame in getting that wrong, I think. So the units are seconds squared, so that's correct for what I did here. Fundamental base units are always very fun questions. Feel free to go back and watch that if you want some advice on how to do that. Determine why. I'm sure they will have done something different. Oh, I got it dead wrong. Huh. Oh, I got that dead wrong. Wait, what? Oh! God damn it, guys. I did not read this graph properly. Again, look at my exam technique. What am I doing wrong here? The values are plotted using different vertical axes. So I read the M2 intercept as being that when it should have been that. I got that dead wrong because I did not pay attention. So clearly my brain is in a false sense of complacency. You're like, oh, guys, I'm going to be completely fine. And look at that. As soon as you think you're fine, like whatever, it's just going through motions, that's when these execution errors slip in. That's when you start to like not spot the traps, when you lull yourself into thinking you're safer than you are. So M2, I should have measured the intercept from there, and then my simultaneous. Okay, so let me rerun this. So that is true. What I missed here is that. So that's wrong for the 4Z. That's right for the 2Z. But actually, this one here is 179.65 grams equals 4Z plus Y. What's the difference between the two lines on the graph? Apologies, I know you joined late, so you missed when I was doing this. What they do here is they've added extra weight. They've added extra magnets. And so we're trying to work out the mass of the yoke, which is this light gray thing, versus the magnets, which are the dark gray thing. So here, M1 is the one with 2 magnets. M2 is the one with 4 magnets. And by measuring the intercepts, because we got given a relationship here, when the current is 0, there's no extra force. So the mass that you measure is a true mass. So here, when I is 0, sorry, not that one. What am I talking about? So let me go through this again in detail, right? So what's happening here? We can see that the current is changing the mass. When the current is 0, we have the true masses. So the true mass of the yoke plus 2 magnets is 134.85 from the M1 axis. And the true mass of the yoke plus 4 magnets is equal to the intercept there with 0 current as measured on this axis, which is 181.85 grams. And that is equal to 4 magnets plus the yoke. And then we can use simultaneous equations in order to work this out. So if we double this up, 134.85 times 2 is, so 269.7 equals 4Z plus 2Y. That was correct. But then if I subtract this, so in fact, I'll write this above. So if we subtract these two equations, so that minus 181.85 is 87.85 is equal to Y. And that's what I should have got. And that's correct. Did I also miss something in the question No, that's fine. So what I missed here was the fact that I had to use the different scales. One for the 2 grams, one for the 2 magnets, one for the 4 magnets. And what I'll do, because you're here, like as I'm marking, I will also give you some indication of what happened in the question, to sort of help you out. Now on this one, just to give you some background, they placed the copper rod in the wrong part of the experiment, and we had to work out what that was going to do to the straight line. I argued that there would still be some magnetic field, but that it would be weaker, which means that this gradient would be smaller. But because everything else is the same, you're using the same number of magnets. I think it was the same number of magnets. Because it's the same number of magnets, the intercept should be the same, but that the gradient should decrease. And B is less, great. And explains why, great. Have to explain why the intercept is the same, because they both have 2 magnets. 2Z and Y, great. Mass of the yolk and the magnets, because same 2Z plus Y. I'm really glad I went back and added that. Why the line is less steep, because it's the magnetic field is less. Yeah. Okay, so I think I'll give myself that. So I think I got that. What does that mean? Because sometimes I say 2 things. Oh, interesting. Hold on. So what I'll say is I've now marked up this paper. I would say the main source of, because remember, when analyzing your sources of error, I split them into conceptual, execution, and exam technique. For me, my main source of marks lost here was exam technique. So I knew what I was doing and I knew how to do it, but I wasn't reading the question carefully enough to know how to apply my skills to get the marks that they asked for. There was a bit of conceptual stuff, revising my experimental protocols. Execution, I think, was okay by and large, but it was mainly losing focus and not paying attention to the traps. And this paper is full of traps. And so those are my main takeaways from this run. Now we have a common question, which I will also do my best to answer. Let me get my Miro whiteboard back up, because I think that is the best way to explain what you're asking about. So we've had a question about, okay, so your question was about this. What does this mean? And from the way you worded it, I think you're talking about piecewise functions. 2 equations or more lined up vertically besides that. So for instance, like systems. So let's talk about this. So let's say we have a piecewise function where f of x is equal to let's say 2 minus x when x is less than or equal to 2, and it's equal to I don't know, something x squared. Let me come up with one quickly off the top of my head. Minus 3x plus 2 for x is bigger than 2. So you might see something that looks like this. And what that means is that's a piecewise function telling you what the function is in different parts of the graph. Do let me know if that's not what you're talking about. In the meantime, I'll explain kind of what this is and how to use it. So if I were sketching this function, I would understand that up to x, when x equals 2, y equals 0, this is going to be linear up until then, with an intercept of 2, and then it goes to 2. And then let's consider, good. So now let's consider what this quadratic would have been in isolation. If I sketch this quadratic in isolation, it would have been x minus 1, x minus 2, which would have had intercepts of x equals 1 and x equals 2. So it would have looked something like this. 2, 1, 2. However, we know that this graph does not exist below x equals 2. It only exists above x equals 2. So then it's sort of doing a quadratic going up here. So in other words, it's only valid for the domain that is listed for that part of the piecewise function. So in other words, this straight line does not exist past the point x equals 2, and this quadratic does not exist before the point x equals 2. So hopefully that makes a bit of sense. It just means that they're linked, and in this case, they have to give you these domains so you know which x ranges these are valid for. Great. So hopefully that's all been very demonstrative. I'll go up, I'll edit, because I know there was some there was a bit in the stream where I had to sort of pause and work on some of my tech. But hopefully that's a good introduction to how to do these sorts of papers, where it's really paying attention to units, to axes, to precise wording of questions. And what I'm going to do is I'm going to spend my afternoon stream today, I'm going to be going through how to use, how to go through uncertainties and how to get things into straight lines to plot and what you can do with those. Because I think those are the two most important skills for a practical paper like this. All right, brilliant. So we're going to stop there. You're very welcome, man. Welcome to come back anytime and ask any questions when I go live. So I'm going to log back on at 5:30. We're going to go through that stuff. In the meantime, take care, have fun, work hard, and I'll see you then. All right, see you then. Bye-bye.